So in the previous slide we saw our fundamental identity. Cosine squared plus sine squared theta is equal to 1. And to wrap up, what we'll do now is derive a few consequences from that. So first of all, let's divide this formula by cosine square of theta. When we do that, what we get is cosine squared theta divided by cosine squared theta plus sine squared theta over cosine squared theta is equal to 1 over cosine squared theta. This right here is 1. This right here is tan squared theta. And the right hand side becomes secant squared theta. So this is equivalent to, and of course here we have to make a small caveat, this only works if cosine theta is not equal to 0. So then our formula becomes 1 plus tan squared theta equal to secant squared theta. Likewise, on the right hand side, what I'll do is I'll take the formula again, and now I'll divide, so I'll take our formula and divide by sine squared, and again we have to make the caveat that only works if sine theta is different from 0, otherwise we divide by 0 and mathematicians get angry at us if we divide by 0. Cosine squared theta divided by sine squared theta plus sine squared theta divided by sine squared theta, that's equal to 1 over sine squared theta. This now becomes cotangent squared theta. This is 1, and this is cosecant squared theta squared. So if we write that a little bit more cleanly, we get that 1 plus cotangent squared theta equal to cosecant squared theta. So that gives us yet another trigonometric formula relating these functions. So now, why are these identities useful? Well, what they allow you to do is, given some of the trigonometric functions, what you can then do is derive the other trigonometric functions from them. So as an example, suppose we don't know theta, but we know cosine theta. And we're given that cosine theta is equal to minus 4 divided by 5. And we also know that theta is in quadrant 3. Find then sine theta and tan theta. So that's our assignment. So let's maybe make a brief sketch as to what we have. So we know that cosine theta is some negative value, minus 4 divided by 5. And we also know that theta is in quadrant 3, that's the lower left corner here. So if we draw this radius, then the angle that we want to find, or that we want to say something about, is this one right here, theta. And using our formulas, we'll be able to find sine theta and tan theta without having to first calculate the value of theta. So what we can do is, we can use our master formula. So we can use the fact that cosine squared theta plus sine squared theta is equal to 1. And we can plug in the value minus 4 over 5 for cosine theta, because that's what we're given, is 1. So this is 9 divided by 25. And in other words, we have that sine squared theta is 1 minus 9 over 25. Ah, sorry, that's wrong. Not 9 over 25. My apologies, 16 over 25, 16 here. And then 1 minus 16 over 25. That is 9 over 25. So moving on, if we then take the square root, we get that sine theta is plus or minus 3 over 5. So we get, again, two potential solutions, but now we're going to use the other part that we haven't used of the problem, namely that theta is in the third quadrant. So, quadrant 3. So, sine theta, if you look at, so sine theta is the y value, and you see all the points in quadrant 3, they have negative y values, so negative signs. So here also we have to choose the negative value. And now the last part is finding tan theta, tangent. That's not difficult. That's just the sine divided by the cosine, and that's 3 over 4. So you see, with a little bit of algebra, given one piece of information, you can find the other pieces. And last thing that we'll do now, before moving on to the next set of lecture videos, is we'll introduce a couple of basic identities very quickly. These are simple identities that you can also use to simplify trigonometric formulas. So the first set of identities that I want to introduce is what happens if you add 2 pi to an angle theta. So if I draw a mini unit circle here with an angle theta, what we saw in one of the previous videos is if you take theta and you add 2 pi to that, you go around the circle once, but you end up at the same point. So you stay at the same point P. If the point P stays the same, then the coordinates stay the same. If the coordinates stay the same, then cosine and sine stay the same. So what we can conclude from that is that cosine theta plus 2 pi is equal to cosine theta, and sine theta plus 2 pi is equal to sine theta. And of course, if you can add 2 pi, you can add 4 pi, 6 pi, you can subtract 2 pi. But basically, you have to keep in mind, adding 2 pi or subtracting 2 pi to an angle gives you the same trigonometric functions. The second set of formulas that I want to introduce are the so-called even-odd identities. And for that, I'm going to draw a slightly bigger figure. So here I take a point P with coordinates x and y, an angle theta. And now what I'm going to do is I'm going to reflect that point across the x-axis. So I'm going to take my entire unit circle and rotate it 180 degrees across the x-axis. So what that does is that gives me another point that I get by going down like this, point that I'll call Q, and I'll draw the radius like that. And when I do that reflection, the angle theta stays the same in value, but it becomes minus theta. And what happens to the coordinates of the point P? Well, you can see the x coordinate here that stays the same, but the y coordinate here, that turns into minus y. So that's all good and well in terms of coordinates, but what does that tell us about the trigonometric functions? Well, we know that the x value is cosine theta, and we said if we do that reflection, theta becomes minus theta, but the x stays the same. So we get that x is cosine theta and equal to sine theta. So from that reflection identity, from the fact that both P and Q, their x coordinate is this segment right here, we get that cosine theta is equal to cosine minus theta. Likewise for the y coordinate, if we look here, we have that this length, the y coordinate as sine theta, and then down below here, we have that this is minus sine theta. And now if you look at sine minus theta, what you see is that that's equal in magnitude to sine theta, but it has the opposite sign. So this is minus sine theta. And this gives you a couple of simple identities to also simplify trigonometric expressions. So for instance, let's do two quick examples. If I ask you what is sine of minus pi over 4, and use this identity, you say it's sine or minus the sine of pi over 4, or minus square root of 2 divided by 2. Another example to use the first identity, if I ask you what is the cosine of 2020 times pi, well, you can pull that apart a bit to say that's pi plus 1010 times 2 pi. Multiples of 2 pi don't change the value of cosine, so that's cosine of pi, and that is equal to